Okay, welcome to momentum analysis. We're going to start doing some linear momentum analysis in this problem. And I always introduce momentum in concert with energy because, I mean, it's very, very rare that you would just use momentum analysis on its own ever for any physical scenario. It would just be one of the tools that you use, and something that you might use along with it would be using energy analysis. That would be common. So I do a lot of those kind of problems, and this is one. So for this problem here, let's just take in the scenario first. It's a little bit complex. So we have this bullet of mass m prime. So we're given the mass of the bullet. It's traveling horizontally with some velocity v prime. So this is supposed to be a v prime right there. Um, and it is fired into a wooden block. So go ahead and try to just see this scenario here. So this is v prime. And the wooden block is initially at rest. So it's fired into the wooden block. It actually goes clear through the block. I'm trying to show that in this middle picture here. It goes through the block and emerges at a speed v prime over 3. It sets the block into motion. And I'm going to say that they don't tell us, like, sets the block into motion at what speed. We don't know. But I want to call that something. So I'm just going to call that v double prime here, just to name it something, because we're going to need to use that. The block then is the bullet goes off, whatever. Then the block um, slides to rest, and we're told that because it's on a surface, which there's friction at that interface, so it slides to rest over some distance s. That's also given. So notice our givens are the two masses. This is v prime and s. So what we're asked to determine here, the coefficient of kinetic friction between the block and the surface, sure, the decrease in kinetic energy of the bullet, we'll do that as a percentage, and the kinetic energy of the block at the instant after the bullet passes through it. So you can see that we're definitely still engaging with energy here. So at first it seems like this mu k is fairly simple to find, right? This block is in motion and then it comes to rest through some displacement s. We know we can find the work there. We can use work kinetic energy theorem even. You could use energy analysis. That feels like it's very doable. The issue is that we don't know this v double prime, right? That's not given in this problem. So in order to find that V double prime, then you might say, well, can we just use energy analysis to find that? We can't, because we just don't know anything about how this bullet goes through the block. So the bullet goes through the block, and it's really, I mean, you could say that it's like the kinetic friction between the bullet and the block that starts the block into motion. And we've seen problems before where kinetic friction is friction that does positive work, right? So this is another one of those cases. The reason we can't just use energy analysis is that this was messy when this bullet is going through this block. There was nothing clean about it. We don't know the coefficient. We don't know how big the block is. We would need a lot more information in order to use energy. Then you might say, well, why don't we use force analysis on it? Again, for force analysis, things need to be really well defined. We would need to know what the forces were, right? Inside there. And again, this is a messy situation. So these messy scenarios are scenarios where we often will turn to conservation of momentum. Conservation of momentum that is something that we only use when we either can't use energy analysis or force analysis. So force analysis is your gold standard of analysis. It is the tool that you use that requires the most information, but it also yields the most information because you can yield vector quantities from it. Energy analysis is, I'd say, probably a step below that. You're dealing with mostly scalars when you're doing energy analysis, so you don't need quite as much information, but you also don't yield quite as much information from doing energy analysis. I can find speeds, not velocities, for instance, doing energy analysis. So in a that's those are the first two tools we would always turn to when looking at a physical scenario. In this one, neither one of those tools is going to work for us because of the inherent messiness of the bullet embedding itself through the block like it does. So this is a perfect case for conservation of momentum. And I want to remind you what conservation of momentum is about. Really, it's was originally how Newton had written his second law. right? So we often think about Newton's second law as F equals ma. But what about, or sum there of external forces, ma? But you can also think about this as being equal to change in linear momentum. Remember that linear momentum is equal to mv, the product there, and it's a vector, right? Momentum's a vector. We're only talking about linear momentum. I'm going to refer to it just as a momentum. Toward the end of the quarter, we're going to approach a topic, a quantity called angular momentum. So when I call it linear momentum, it's just to differentiate it from angular momentum. So if I see this dp dt, then really I can see this as m dv dt, which is the same thing, right, as ma. So this really tells you about momentum as a quantity and what this is about. So if we know that the change in momentum, any change in momentum is going to be equal to the sum of external forces, what this tells us, like if we run this backwards, it tells us that if my sum of external forces are zero, my change in momentum is zero. So when people say like, "Oh, conservation of momentum, momentum's always conserved." No, it's not always conserved, right? We have acceleration all the time. But in a case when we're talking about conservation of momentum, we say, well, if we can define our system such that external forces sum to zero, then I can lean on this and I can say, all right, my momentum, then I can say the change in momentum will be equal to zero. So let's kind of play around with this and see how this would apply to this problem. I'm going to give myself a little more space here. So I'm using a combination of momentum and energy analysis. But in order to find this V double prime, I have to use momentum analysis. So let's say here, our first job is to determine V double prime. Once we have that, I know I can use energy analysis to find that coefficient. And I've done that a million times, right? So we're going to use momentum analysis here. What we can say then, and let's talk about this, like what is our system? The system that we're using is going to be the system of the bullet and the block, both. The reason it's important to define this system is then all the messy forces of the bullet and the block interacting as the bullet makes its way through the block, guess what? Those are all internal forces if I define my system like this. So that's awesome. That's really fantastic. Then I can say, well, can I really make the case for the sum of external forces to be zero? Can I really make that case? Well, if I look at the bullet and block scenario, I could say, well, the block does have other forces on it. It has weight downward and it has normal force upward, but those are going to sum to zero, right? It has the force of the bullet on it, but that's an internal force since my system is about both bodies there. And then I can look at the bullet and say, well, I don't know, when the bullet's flying through the air, it's definitely under the influence of gravity there. We'll ignore air friction right now. But what we say for applying conservation of momentum usually is like, okay, we can kind of say, because this happens fast enough, like as long as the delta t, the time frame is really, really short, I can make the argument that um, basically I can neglect the gravitational force on the bullet. I couldn't do that if I was counting on the bullet going over some long distance, right? Where it would definitely follow a different path. But for this one, I can say, I'm really just looking at this tiny, tiny time window. And this is characteristic of momentum analysis. I'm going to say this again. It's characteristic of momentum analysis. When we use momentum analysis, we are generally analyzing an event. That event generally takes place over a very short period of time. Notice that with energy analysis and force analysis, we're generally analyzing processes, right? That take place over distance and over longer windows of time. When you're using momentum analysis, in general, you use that for something that happens quickly, a collision, an explosion. So something like this qualifies as a collision, and it would happen very, very quickly, a fraction of a second. So we can say that means that we can make the case for net external forces for the system to be zero. do that every time before you decide to use conservation of momentum. It's one of these things that, like, you have the hammer in your hand and everything looks like a nail. You just can't use it on everything. That generally means that you don't understand how it works. Okay, but we can use it for this collision, right? We've just sort of justified why we can. So let's look at the initial momentum. And I'm going to put a sign convention on this scenario. I'm going to say rightward positive. This is nice and simple. Everything's moving to the right. So initially, my momentum is just, this is before the collision, right? So before the collision, where's my momentum? It's just in the bullet. So mv prime, this is positive. I have rightward positive. After the collision, where's my momentum? Well, now part of it's in the block. So big M, V double prime. And then the bullet still has some too. Little m, V prime over 3. So I made my arguments above why external forces, I can say that those are equal to 0. And what that means is that I can set my initial and final momenta equal to each other. So I have mv prime is equal to big M v double prime plus little m v prime over 3. All right. So that is an example of applying momentum analysis. If I do some algebra here, what this is going to render me is v double prime is equal to 2 m prime v prime over 3 big M. Okay, right, the bullet mass is little m prime. I realize I dropped those primes. And the wooden block is mass big M. Okay, so good. I've got my v double prime now. So now I can use energy analysis to determine mu sub k. Okay, now I'm all over that piece of it. So this is just a block that was moving at v double prime and it comes to rest over some distance s, right? I've totally got that. So I'm going to use final energy minus initial energy equals work done by non-conservative forces. In this case, that's just friction along the interface between the block and the horizontal surface it's resting on there. So my energy final um, for the sliding block is 0. My energy initial for the sliding block is 1/2 m v double prime squared, and I know I can express v double prime in terms of givens, equal to the work done by friction. So now I'm going to do a quick free body diagram of the block as it's sliding. So this is the sliding block. And as the block is sliding, what's going on with it? Well, we've got weight, we've got normal force, and we have a force of kinetic friction. And my displacement is, of course, to the right there. Okay, so that means that I can express the work done by friction as negative mu k and s here. Negative because that is going to give me a cosine 180 degrees, which is -1. The normal force is equal to the weight of the block in this case. They're on a horizontal surface. There's no vertical acceleration and no other accelerations, or sorry, no other forces in the y acting at all here. So actually what I end up with here is um, 1/2 mv double prime squared is equal to mu k mg s. Okay, so that's another equation. All right. So that will allow me to find my mu k. I can sub in for that v double prime and I can solve for mu k. So that part A is basically done. Part B asks us then the decrease in kinetic energy of the bullet. So, and I guess I'm not really clear in this problem about what I'm asking for. But I guess I don't ask for a percentage. I'm asking like what is the amount of decrease. So I think maybe that's what we're after here. So let's look at part B. And we want to look at the change in kinetic energy for the bullet. So that's going to be kinetic energy final minus kinetic energy initial, right? So my final kinetic energy for the bullet, remember, we're not talking about the block here. The final kinetic energy for the bullet is 1/2 m prime v prime over 3 squared. And initial kinetic energy for the bullet is 1/2 m prime v prime squared. So that is what my change in kinetic energy is, and that's what this particular problem is asking me for. Um, so in this problem, I think I can just do this math and find what my decrease is. If I do this arithmetic here, I'll end up with negative, it's a decrease, so that makes sense, 49 m prime v prime squared. So that's the change in kinetic energy. So just thinking about the language is asking me how much the decrease is. So I can say, um, so K decreases by 4/9 m prime v prime squared, right? This is how big the decrease is. Okay. And then part C asks for the kinetic energy of the block at the instant after the bullet passes through it. And that probably is fairly trivial at this point. We have this V double prime here, right? So we know the mass of the block, so we can find the kinetic energy of the block right at that point.